last concept we're going to take a look at with respect to these elementary vector fields is we're going to take a look at the idea and the relationship between a conservative vector field and the idea of a potential function. A vector field is said to be conservative if the gradient of some scalar function, if it is the gradient of some scalar function. So that means that there is indeed some vector field f that's going to be equal to the gradient of some function f. Now this function f is going to be called the potential function. All right? So really del f is going to be that phi of xyz, and phi of xyz is the potential function. And later we're going to see that idea of potential energy, and we're going to turn that into a conservative vector field. And we're going to talk about what it means to be conservative, and we're going to talk about what it means for a vector field to be conservative, and we're going to talk about independence of path later. And they're all interrelated. Probably things that you've heard in your physics courses, but if not, this is going to be a pretty good eye-opener to the relationship between these partials and the respect to those vector fields. A very elementary example, one that's used all the time, is in physics at least, electromagnetism, is this vector function fxyz is equal to negative mmg x divided by x squared y squared z squared 3/2 I, and then it's the same thing except instead of x it's replaced with y and z, and I is replaced with j and k. It's a gravitational field. We're going to verify that the vector field is conservative and it has the potential function mmg over the square root of x squared plus y squared plus z squared. Right? So here's what we're going to do. We're going to start by taking the partials. And to do that, we're just going to rewrite this as x squared plus y squared plus z squared to the minus 3/2 power. Or minus 1/2 power, excuse me. We haven't taken the derivative yet, so we can't necessarily say that. And now what we're going to do is we're just going to find phi sub x. Now, mmg are constants. Okay, so all we're going to do is we're just going to move the 1/2 in front. Okay. We still have mmg. We're going to subtract 1 from the exponent, and then we have a chain rule, so we're going to multiply that by 2x. Right? And if we were to simplify that just a little bit, the 2 and the negative 1/2 would simplify into negative 1. We're going to move the negative exponent back down to the denominator, and we're going to get the opposite of mmgx divided by x squared plus y squared plus z squared to the positive 3/2 power. And that's exactly the coefficient if we look back at the vector field, the conservative vector field that we're trying to show. That's exactly what we get for the coefficient of I. So far we're on the right track. Now, as you can imagine, we could just replace the x each time, because it's going to be the same mechanics to be able to find the partials. We can replace the x with y and z respectively. So phi sub y, we're going to have the exact same derivative, negative mmg, except the chain rule is going to give us a 2y. Okay. We still have the 1/2, so the negative 1/2, and that's going to be x squared plus y squared plus z squared to the 3/2 power. And that's exactly what we wanted, because if we go back up to the definition, that's going to be our potential function. Finally, for phi of z is going to be the same thing, minus mmg, this time of z, divided by x squared plus y squared plus z squared to the 3/2 power. All right. And so what we've done is we've taken the partials of this potential function phi, and we've shown that it's equal to that gravitational field, that conservative vector field at this point. And so is indeed the potential function. It's going to be more difficult later when I give you the vector field, and we're going to go back to find the potential function. All right, we're only going to be given one or two of those, so we have to go back and we have to go reverse and find those vector fields. All right, so if I give you a potential function, then all you would have to do to be able to find the if I give you, the potential function, then it's very easy to find the conservative vector field. So all we're going to do is we're just going to find phi of x. All right, in this case, phi of x, the derivative of arctangent is 1 over 1 plus x squared. So it's going to be 1 over 1 plus xy squared. But then we're going to multiply that by the derivative of inside with respect to y, x, which in this case, xy, which is going to be y. Phi of y is going to be the exact same thing, except we're going to multiply by x. And now that we have those two partials, we can very easily figure out what the conservative vector field is for that. All right, so we're just going to stick an I and a j in front of those, and so our del f, or we could just call it f, even though it's del f. So del f, which is going to be equal to f, which is conservative, is going to be equal to y over 1 plus xy squared I plus x over 1 plus xy squared j. All right, so that's our conservative vector field. Right. We can even do it with a function in 3 dimensions. All right, that has 3 variables in it. So, and remember at the beginning when we took a look at the idea of what it means to be a vector field in 3 dimensions. We're just going to have an x, y, and z direction for our potential function, or for our vector field once we get it from the potential function. So, now phi of x is a little bit more difficult this time because it's going to be a chain rule. Okay, so phi of x is going to be 1 sine of xz plus x cos of xz. And then we're going to multiply by the derivative of the inside with respect to x. So from our chain rule, that's going to give us a z. Okay. Even easier, phi of y, that's going to be 0. And then phi of z is fairly easy. We don't need a product rule for this derivative. The x is constant. The derivative of sine is cosine. But then we still have a chain rule, so we're going to multiply that by the derivative of the inside with respect to z, which is just going to be x. So another way to write that would be x squared cos xz. Okay. Finally, we're going to write what the conservative vector field is. All right. So we're just going to take those partials, and so our gradient f, right, which we're just going to call f, is going to be equal to, so remember, we had sine of xz plus xz cos xz, and then we're going to multiply that by the I, because now we have our vector field. So notice that all I did was I just took the derivative that we had with respect to x. It's a 0y, or 0j in this case. And then finally, we have that x squared cos xy k. And that would be the potential function. I'm sorry, that would be the conservative vector field from that potential function. All right. Now, like I said, later what we're going to do is we're going to show what the significance of this is. Okay, but for right now, all we're doing is we're just getting through some of the most basic operations: plotting, understanding the relationship between level curves, as well as vector fields, or some sort of the gradient function, and then the gradient function with respect to potential functions.